All right, we'll start our study of thermodynamics quite appropriately by looking at the first law of thermodynamics, which says essentially uh, energy, the change in energy is equal to whatever energy comes in minus whatever energy goes out. Well, we can look at the two parts of the word and see that it is the connection between heat, that's thermo, and dynamics, which is the study of force and work. So what we're really talking about is how do we turn heat or stored thermal energy into some kind of work? How do we make a car move with gas? How do we turn a turbine with natural gas or with um, some other form of heat? So the place we start is what's called the first law of thermodynamics. Um, And that first law basically says that the amount of um, heat transferred into a system, which we're going to call Q, uh, combined with the amount of work done by a system is going to equal the change in energy. Okay, so we take this guy over here, right? He takes in some food. Um, and then that's going to be basically food energy that he's adding to his system, right? And then he's going to lose some thermal energy, Q, and then he might do some work, right? And so him doing work is going to cost him some energy as well. And so the change in energy of the whole system is basically how much food energy minus the work that this person does minus the heat loss. So that's in some ways pretty intuitive, right? The tricky thing is the sign of work can throw people off. But really, if you think about it physically, you can always come back to, okay, is the energy going to change? Well, if I add heat energy, it's going to go up, right? If I take away heat energy, it's going to go down. If the system does work, if this person or whatever system does some work on the environment, then that's going to cost them energy, right? So it's going to be a minus. And if work is done on the person, that makes less sense with the person. But if work is done on the system, then it can actually add energy to the system. So we can write this like this, which I've always found to be a little easier way to understand it. You can add energy through heat or work, and you can take away energy in those same two ways. So when we talk about the first law, we're interested in total changes to the system. And the reason that is because internal energy is path independent. If I have a system with a certain amount of energy, uh, it doesn't matter how that energy got there. It's going to look exactly the same. Okay, and because it's going to look exactly the same, we can be less concerned with exactly how it got there and how it changed. So we look at this system here, and we start off with the same system, and then we have two ways that we can add 9 joules of energy, right? In this, on the bottom, we're doing work on the system that's adding 159 joules in, and 150 joules out is going out through thermal change. And so the system has 9 joules more energy than it did initially, right? In that a more complicated system up here, right? We have some heat coming in, we have some heat going out, we have some work coming in, we have some work going out. Ultimately, we have 15 joules of heat net coming in and 6 joules of work going out. And there, we have plus 9 joules overall. The end system here, and here are identical. Okay, so if the systems were identical to start with and they had the same change of energy, there's nothing in the system that could make us know how the energy got in or got out. Okay, so that's a key idea in thermodynamics. It's something to keep in mind. We're really interested in states of systems and less interested in the process which gets us from state to state.